Hi everyone, I'm Regina and this is my Lab 5 on the falling Slinky. For this lab, I've split it up into the introduction, which is where we'll talk about the purpose of the lab, models and principles, and the summary. And for the experiment details, I will go over the experiment itself, code, discussion, and conclusion. The purpose of the lab is to determine the effects of gravity and drag on the motion of the Slinky, and to use Tracker to analyze the motion of the Slinky with respect to position over time, and then to predict the motion of the Slinky using a computational model. And in this lab, the system is the Slinky and the surroundings were Earth's gravity and drag. Some models and physics principles used were force due to gravity, the velocity and position update formulas, weight force, drag force, and the tension of the Slinky. The methodology behind this experiment was to create and edit a computational model based off the fundamental physics principles to create and contrast observed data and the predicted computational model using the tracker data and the computational model data. The following are the preview of my results. The initial position was 0, 0, 0 at frame 65. The mass of the Slinky was 0.204 kilograms. The final position was 0, negative 1.668, and then 0. And this was at frame 675. And another thing to note was that when this video was recorded, it was at 300 frames per second, and the height was calibrated to the man on the right, and he was 1.75 meters. Experiment details. So the following is the analysis of the falling Slinky using tracker, and here the mass was, as I mentioned earlier, 0.204 kilograms, and the object was the Slinky, so it initially starts at 0, and the height was calibrated to the height of the man, which is 1.75 meters. And the reason why the gaps between the frames are extremely large is because the slow motion camera used was recorded at 300 frames per second. For my code, the mass of the ball was set to 0.204 kilograms, which I got from my tracker data, along with the other initial conditions, which are stated in lines 39 and 40. Delta t is equal to 0.01, and acceleration due to gravity is 9.8, and lastly, the drag proportionality constant was calculated through trial and error. Now for the rest of my code, this is split up into two parts, which really is just two while loops, and the first loop is set to run until the top of the Slinky reaches the bottom of the Slinky, and for this part of the code, I applied the weight force, tension force, and the position and velocity update formulas. And in this code, the forces cancel out, which is why the bottom of the Slinky is stationary. For the second while loop, I edited the time of observation from my tracker data, and drag is included in the code because the Slinky is now moving down, so the bottom part of the Slinky is now falling to the ground, and the velocity and position update formulas are also included here. Now for my results, I took my tracker data and the computational or the predicted model data, and I put it into one graph. So here we have the observed position versus the predicted position, and the predicted position lines up pretty well with the observed except for towards the end, and the first few seconds of the graph line up perfectly because the bottom of the Slinky was not moving, so it was stationary. And at 7 seconds, the top half collided with the bottom half. You can see how they're literally on top of one another. And that's where the bottom half of the Slinky started to fall. Another thing to note are possible errors. One of them could have been on my end when I was plotting the data points in tracker. Another could have been when calculating the drag force constant. If I calculate that incorrectly, that would have caused a slight discrepancy. Or the low frame rate from the video that was put into tracker, that could have caused miscalculations. Now, one thing I want to talk about is why the bottom of the Slinky was stationary. What does this mean? So what this means is that the tension and gravitational forces are equal, meaning that because these two forces are acting on the Slinky, they are opposite and equal, so the Slinky remains in this stationary state. Ultimately, the bottom of the Slinky didn't move because when it was released, there was no net force acting on it. And through this lab, I was able to create a computational model to predict the motion of the Slinky, applying concepts such as weight, drag, and tension forces in addition to Newton's second law of motion. Thank you.